Okay, so today we're going to be talking about the differences between mass and weight. So let's just jump right into it and define the two. So mass is defined as the amount of matter, whereas weight is defined as a force of gravity. Mass is measured in kilograms, whereas weight is measured in the unit newtons, okay, which we give the symbol capital N. Mass doesn't change with location. In other words, the amount of matter that you have doesn't change no matter where you go in the universe. So it doesn't change with location. Whereas weight depends upon the gravitational field strength. So if you go to an area that has a different gravitational field strength, you're going to have a different weight. So this does change with location. Okay, and I'm not talking about where you are on Earth. I'm talking about what gravitational field strength you are in, what different gravitational field you're in. Okay, so let's kind of review what we did in our activity, the mass and weight activity. We had mass, which we measured in kilograms. We measured the weight of the different masses using a spring scale, and we plotted the relationship. And we saw that there was a linear relationship between the two. And we started talking about what the slope represents. And we saw that the slope was approximately 10 newtons per kilogram. And we saw that, hey, this number looks familiar. Okay, and we defined the slope as g, which g represents the gravitational field strength of the planet you're on, which the g on Earth is equal to the 9.8 newtons per kilogram. The g of the moon is equal to roughly 1/6 that, or 1.7 newtons per kilogram. And we'll talk more about later on where this number comes from, or what is this related to. So if we put together the equation for this graph, it's a linear graph, so all linear graphs follow the equation of y equals mx plus b. And it makes sense that we have a y-intercept of 0 or something very close to it, because if there's 0 mass, there's 0 weight. So we have the weight on our y-axis, we have a slope that's represented by g, and we have mass on our x-axis. So rearranging this, it's typically expressed as f of g equals m times g. So if you want to find the weight of something, you take the mass in kilograms and multiply it by the gravitational field strength of the surface that you're on. So this actually answers a lot of questions, okay? Specifically of why all objects, regardless of mass, accelerate at the same rate, okay, if air resistance is ignored. So if we have two masses, mass big M and little mass little m, the little mass is going to have a little weight, whereas the big mass is going to have the larger weight. So if we set up Newton's second law for both of these, A equals F net over m, okay, well in this case m is big M, and for the small mass we have the mass little m, that this is little m times g, because if they're in free fall, the only force acting on it is the force of gravity, so little m times g divided by little m. And for the big mass, this is big M times g divided by big M. But you can see in both situations you have m divided by m and big M divided by big M. The m's cancel out, and the acceleration of the object is g in both cases. Okay, the large body has a greater force pulling it down, but it also has proportionally a greater mass. So it has more force but more mass. This has less force but less mass to accelerate. So they both are accelerating at the same value. Okay, and this is true for all objects that are in free fall. And this just kind of proves why. So let's do a little example here. So Frodo is standing on a level surface. He has a mass of 46 kilograms, and we want to know what his weight is. So F of g equals m times g. So we have the mass of 46 kilograms times the gravitational field strength of 9.8 newtons per kilogram. So if we calculate these two, or multiply these two, we get 451 newtons. But what's more important is if we draw the free body diagram, we have a downward force of gravity, we have an upward normal force, and if he's at rest or moving with a constant velocity, those two forces are balanced. So if the weight is 451 newtons down, then the normal force is also 451 newtons, but pointing in the upward direction. So if you know the weight, you consequently know the normal force as well. And these two are equal if there's zero acceleration, which, remember, zero acceleration is not moving, okay, or moving with a constant speed. All right, so that's all for now. We'll talk more about some additional problems tomorrow, and that's all for now. Have a good night. Bye-bye.